Today is day 10 of Unit 4. We started today with a ticket in the door, so if you were absent, please make sure you make that up. And then we did a warm-up. So pause the video, try the warm-up, and then play to check your answers. So the first one, we can take 5,406 and divide it by 4 to figure out how many times through the cycle and what the remainder is. But actually, anytime you have large exponents like this, you really only care about the last two digits and how many times 4 goes into that, or what's the remainder. So I really only actually have to divide 6 by 4, and it goes in one time, and the remainder is 2. So this is equal to I squared, and I squared is equal to -1. Next, first, outer, inner, last, or generic rectangle. So 2 times 2 is 4. 3i times -3i. Oops, 3i times -3i is -9i squared. 3i times 2 is 6i. And 2 times 2 is 6i. 3i times 2 is positive 6i, and we didn't do negative 3i times 2. We didn't do the outer, so that's negative 6i. So the positive 6i and the negative 6i cancel out. Negative 9i squared simplifies to positive 9 because it's -9 times -1. And 4 plus 9 is 13. 13 is the final answer. Number 2, we first have to figure out what the discriminant is. And the discriminant, remember, is b squared minus 4ac. So substituting in the values, p squared minus 4 times a, which is 2, times c, which is 5. And that discriminant has to be greater than 0 in order to have the two real solutions. Remember, the part underneath the quadratic formula has to be positive. So p squared minus 4 times 2 times 8 is -40. So solving that, p squared is greater than 40. If I add 40 to each side, square root of each side, I get the absolute value of p is greater than, I'll simplify that, 2 root 10. And then to get rid of the absolute value when it's an absolute value greater than, remember that's or, so p is greater than 2 root 10, or p is less than -2 root 10. Those are the solutions. Okay, so just a couple examples today, and the examples, the notes for today are in the packet, so you can find this problem on page 22. It's problem number 5. So this problem needs to be simplified, and the issue, or the reason it's not currently considered simplified, is the denominator has a complex number. Can't leave complex numbers in the denominator of a fraction. Similar to earlier in the unit, we looked at square roots in the denominator. Can't leave those. Similarly, we can't leave complex numbers. So if you recall how we simplified this, we rationalize the denominator by multiplying by √2 over √2. We're going to do the same thing here, well, sort of the same thing, except for we're going to multiply numerator and denominator by what we call the complex conjugate. So you want to write that somewhere in your notes. So complex conjugates, we have a plus bi and a minus bi. So what that means is the real part is the exact same, and the imaginary part's the same except for it has opposite signs. And when you have complex conjugates and you multiply them, what's going to happen is the outer and the inner terms are going to cancel out, and you're just going to be left with the first times the first and the last times the last. In the warm-up, go back here a minute, we had 2 plus 3i and 2 minus 3i. Those are complex conjugates. So what happened there was the outer when I multiplied the outer terms, I got negative 6i, and the inner terms, I got positive 6i. They canceled each other out. That will always happen when you multiply complex conjugates. So when you're multiplying complex conjugates, you can just multiply the first times the first and the last times the last, and you actually don't have to worry about the outer and the inner terms. Again, you can only do that when they're complex conjugates. If they're two binomials that are not complex conjugates, you have to do all four terms, first, outer, inner, last. But for the complex conjugates, that canceling out will always happen. So back to our problem. Complex conjugates is going to help us to simplify this. So I'm going to take the problem here, that what's causing us the issue, not simplified, is the 2 plus I. So I'm going to multiply both the numerator and the denominator by the complex conjugate of 2 plus I, of the denominator. And so when I do that, in the numerator, first of all, I have a monomial times a binomial, so I know I just distribute. So that gives me 8 minus 4I. In the denominator, remember what I said a moment ago, we have complex conjugates, so I can just do 2 times 2, first times first, which is 4, and last times last, I times negative I, gives me negative I squared. I don't have to worry about the 2I and the negative 2I from the outer and the inner, because obviously 2I subtract 2I gives me 0I. So now I can simplify that. I have 8 minus 4i in the numerator, and I'm going to simplify 4 minus I squared, 4 minus negative 1, that's 4 plus 1, which is 5. So I have 8 minus 4i all over 5. That I'm going to do one more thing too. I'm going to break that into two separate fractions, 8/5 minus 4/5 I. And it should be written in that order where you have the real part first and the imaginary part second. And if either of those fractions were to simplify, or both of them, I should simplify them. 8/5 doesn't, 4/5 doesn't, so I'm going to leave it that way. And that's how you simplify when you have complex denominators. Okay, on the same page, let's take a look at problem 11. And I had students try that in class first, so you might want to pause the video here, try it, and then play. So I'm going to go ahead and multiply by the complex conjugate of 3 minus 4i, which is 3 plus 4i, and I'm going to multiply that by itself over 1, or I'm sorry, 3 plus 4i over 3 plus 4i, because that equals 1. So then in the denominator, remember, just first times first, which is 9, and last times last, which is negative 16i squared. But in the numerator, I have two binomials, and they're not complex conjugates. So I have to do first times first, outer times outer, inner times inner, and last times last. So 2 times 3 is 6. Outers, 4i times 2 is 8i. Inners, 3 times I, 3i. And last, 4i times I is 4i squared. So simplifying that, in the denominator, I have 9. Negative 16i squared is negative 16 times negative 1, which is positive 16. In the numerator, I have 6. 8i and 3i combine to 11i. And 4i squared simplifies to negative 4, because 4 times negative 1. So simplifying further, 6 minus 4 is 2, plus 11i, and that's all over 25. Last step, break it into two fractions, 2 25ths plus 11 25ths I. And neither of those fractions simplify, so that is my final answer. Now that was it for examples for today. The rest of class was given to work on these problems. So you'll need to finish up page 22. That's the page we were just working on. And then in Unit 4 in your worksheet booklet, you're going to do worksheet 4, problems 1 through 16, and you're going to do all of worksheet number 5. You do have a quiz coming up later this week on Wednesday on everything we've covered in Unit 4.